So welcome. I'm very happy to have Flaminia Giacomini here today, whose work is in foundations of quantum mechanics and especially to do with its relation to spacetime theory. She has a PhD from the University of Vienna, right? And today she's going to talk to us about some of the issues she's been working on in what we like to think of as tabletop quantum gravity. That's okay. So please take it away.
Okay, so thanks a lot. Maybe I should still point on the... Can you see my cursor? Okay, good.
I'll be by the way, I'll monitor the chat, so if people have questions, put something there, and I'll either, I can bring it in. I can interrupt people if necessary.
Yeah, so I don't see the chat, so it's.
I'll keep an eye on it.
Okay, thanks. Okay, so first of all, thanks a lot for this nice invitation. It's really nice to be here again in person after 2 years of Zoom meetings remotely. So what I'm going to talk about today is work at the intersection between quantum theory and gravity. And this is a relatively new way of thinking about this interface with the tabletop. And I know that many of you are already familiar with this approach. And in particular, what we do here is to take some tools of the field of quantum information and apply them to questions that were typically addressed within a more gravitational context. And so the talk has 2 parts. The first part is this 2018 paper, which is about a thought experiment, a quantum information protocol. And the second part is more recent work with my 2 colleagues, Thomas Galli and John Selby. And this is about the theory-independent no-go theorem. So let me start with a broad motivation. And I want to be very concrete and motivate this. Doesn't change slide. Okay. I would like to motivate this research line with a very concrete and practical, by giving a very concrete and practical motivation, which is an experimental one. So this is a paper from the group of Markus Aspelmayer that came out last year. And what they did was to take these, well, maybe you cannot see them very well here, but these small spheres, golden spheres. So this basically is the size of a penny, and this is the sphere. And they made them interact gravitationally. And they measured the gravitational coupling between these 2 small spheres. And these 2 spheres weigh as little as 90 milligrams. So they're really, really light. And this is the state of the art for what concerns the smallest so the gravitational field of the smallest object that has ever been measured. And so where do I want to go here? So the goal of this research line that Markus and other people also are following is to decrease the mass of the objects of which we can measure the gravitational field. And at some point, we will reach a regime where we can put this mass in a quantum superposition state, in a quantum superposition of being here and there. So now the question that as theorists we would like to address is this a new observational window for quantum effects in gravity? And if so, which regime does it address? Which type of conclusions can we draw on the gravitational field with this type of tests? And so actually this question has a very long history, and we can trace it back at least to Richard Feynman, who at the Chapel Hill Conference in 1957 proposed a thought experiment where he was placing a mass in a superposition and then he was amplifying this effect. And he concluded from this experiment that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. And from this proposal that Feynman made in 1957, there were many people that followed. And so from the 80s, 90s, 2000s, so there were many, many papers also comparing semi-classical gravity and like Newtonian gravity. And I do not have time to mention all of them now, but what I would like to focus the attention on is these two papers, recent papers in 2017 that came out on the same day on the archive. And this revived the debate and put it under a kind of a different light by looking at gravitational induced entanglement. So basically, and using tools of quantum information. So what's the setup here? So you have two quantum systems, we can call them A and B, and these are initially in a product state, but in a quantum superposition, each of them. And then these interact gravitationally, and after some time, via the Newtonian interaction, after some time, they will be in an entangled state. So then the authors of these two papers used the LOCC argument, which is a very famous theorem in quantum information, and states that you cannot generate entanglement just using local operations and classical communication. So they conclude that the gravitational field cannot be a classical channel, basically. And these two results originated a lot of debate, and which revolved around a critical point. And in order to explain it, let me make an analogy. So imagine that you have two particles, this blue one on the left and this red one on the right, and you connect them by a spring. So this spring is basically acting like a harmonic oscillator. So it's an interacting potential of this type. And initially, you prepare the blue mass in a quantum superposition state. After some time, by the dynamical evolution, you will get that these two masses are entangled. And the question now is, does this allow you to conclude that this potential that couples them is a quantum degree of freedom and needs to be quantized? Of course not, it doesn't. But, and then an analogous argument was made for the gravitational field, because since these experiments only rely on Newtonian interaction, this can be described as a non-local potential that acts at a distance. And then it is, in a more formal language, it is a gauge degree of freedom. It is not a real degree of freedom. And then people argued that because of this reason, you cannot conclude anything on the quantum nature of the gravitational field. So what does this mean? So first of all, okay, we can discuss, but maybe this is not the right setting to discuss it, what it means to be a real degree of freedom in the context of a gauge theory. But also a more like looking forward, at the question that we would like to answer, does this mean that we have to give up, that there is no hope with these experiments to say anything about the gravitational field? So that's, I think it's at least a very pessimistic view, and we cannot afford that, because these are experiments that we might be able to realize in the midterm. So what do we have to do? Is this the end of the story? And I would say no. And because we know that there is general relativity, that is a theory that is well established and that has many empirical confirmation. So we can use it. And so we come now to this thought experiment that is the first result that I would like to talk about. So basically what we did here was to take the gravitational version of these two experiments, those two papers there that analyze the electromagnetic version. And so one of the problems with this type of research, with these results, is that sometimes the assumptions are not really clearly stated, and then people implicitly use some notions that they think are natural, but then these notions are different according to the people that you talk to. So let's state our assumptions here. So here we assume that G is a field, so that there is no interaction at a distance. And we also assume a specific framework, which is linearized quantum gravity. So we are within a very specific and concrete description approach to the problem of putting together gravity and quantum theory, linearized quantum gravity. And the regime that we are considering is Newton potential plus retardation. That's all we need. So long before the experiment starts, just to stress that the Newtonian description here in our setting, and we will see why in a minute, is not an approximation, is an exact description for what concerns the generation of entanglement. And this is because we prepare a massive body A in a quantum superposition of being in two positions, say x1 and x2, long before the experiment starts. So we put it in a superposition, we wait long enough so that the field is settled in the whole region that we care about. And then once this has happened and nothing is moving anymore, then we start the experiment. And we start the experiment consider another particle B that is far away at distance D from A, and that is initially localized in a trap. So basically you see now that since nothing is happening here, the interaction is just purely Newtonian because there is nothing evolves, everything is static. And at the beginning, since B is localized in a trap, the full quantum state is the left configuration of A and the gravitational field corresponding, so the Newtonian gravitational field corresponding to the left configuration of A, and plus the right configuration of A, and the Newtonian gravitational field corresponding to the right configuration of A. And then we have this psi0 that you can think as the ground state of B when it's localized in the trap. And now, at the initial time of the experiment, B has a choice. He can either decide to release the trap or to keep the trap closed. If B does not release the trap, then nothing changes. B will just follow this trajectory for the whole time, so it doesn't move, and the state will be this one for the whole time. So notice that B is not entangled with A and G. But if instead B releases the trap, then what happens is that B will start feeling the gravitational interaction of A, and it will start moving in a different direction, so in a different way, according to whether it feels this field or this field. So at the beginning, it will move just by very little, so we will not be able to see any entanglement. But after some time TB, we will have an entangled state that we can write in this way, where you see now that we have a three-body entangled state where B is entangled with both A and G. So now you see that whether B releases the entanglement, the trap or not, then we have either that we have a three-body entangled state or a two-body entangled state. So now A can finish the experiment by recombining her superposition. So by bringing the two, like the particle back together. And it will take her at some time TA to close the superposition. And then the question is, will A observe interference here? And this question is related to what this full state is. Because if B is entangled with A and G, then A will not see interference. But if B is not entangled with A, then A may see interference. She will not see interference for sure, but she may see interference. And so basically, according to whether A sees interference or not, she can know whether B has opened the trap or not. And then the question is, can A know that before a light crossing time? And if she can, then we have violated faster than light signaling. So there is an argument which I think is, we can go through it during the question time, and but for the sake of time, I will not repeat. And the answer is that she cannot know whether B opened the trap or not, but you have to put into this description two elements that are typical of quantum field theory, which are vacuum fluctuations and the emission of quantized radiation. In particular, vacuum fluctuations to limit the ability of seeing, basically, of acquiring which path information, and radiation, emission of quantized radiation, to basically make A decohere if she tries to recombine her quantum state too quickly. So these are the two things that we have to take into account. So the conclusion that we derive from this is that the interaction by the Newtonian field is not as harmless as it seems, but we should consider the state to be entangled with even the state of a Newtonian field as a quantum state that is entangled with A and B. And this is because the quantum, even the Newtonian field has some quantum information content. So the take-home message of this part of the talk is that if we take this linearized quantum gravity approach, then we cannot escape from adding, unless we want to violate faster than light signaling, we cannot escape from adding these vacuum fluctuations and quantum state of radiation to obtain a consistent description of the situation. And then the argument is then the Newtonian potential has a quantum information content, has its own quantum state, and should be considered entangled with the source of the gravitational field. And then if we want to keep a classical description of gravity, then we need to drastically modify the structure of the theory. However, there is also something that this paper does not show. And let's talk about that. So the color is a bit unfortunate, but so basically, we cannot derive conclusions on the nature of the gravitational field from this argument. And I want to stress again that all the conclusions that we derived here are because we assumed a framework for the description of gravity, which is linearized quantum gravity. But there are alternative explanations of this effect, which do not rely on having linearized quantum gravity. And so we are not showing that vacuum fluctuations are the only possible explanation, so that the emission of radiation is the only possible explanation. We are not showing that gravity has to be quantum. We are not showing that we need gravitas. We're not showing any of that. And so the only thing that we are showing is that within a specific formulation, we cannot adopt a fully classical explanation in order to explain this result. So what else can we do if to go beyond this and to be able to say something that is a bit more? So there is also a logical problem, which is the fact that if we want to deduce some features of gravity, then we cannot assume a theory for the gravitational field, because there we're just confirming a model. We're not showing that gravity is has to be in a certain way. So what we need is a theory-independent description. And we want to answer this question, which is that provided that we observe gravitational induced entanglement in the laboratory, which conclusions can we draw on the nature of the gravitational field? And the way, so this brings me to the second part of the talk, which is a theory-independent approach to the gravitational field and to the question of what is the nature of the gravitational field. And there is another result by Chiara-Merletto and Vladkov et al., which is different, however, from ours. And I know that you are aware of it. So let me just go to our result. And we use a different framework to theirs, which is generalized probabilistic theories that I will just call GPTs from now on. And generalized probabilistic theories are a framework which relies on an operational characterization of a physical theory in terms of probabilities. So it's not that generalized probabilistic theories say that we should not care about a more like ontological statements, but since this is what we observe in the experiment, this is the description that we're going to use without assuming, without making ontological commitments. So very like in one slide, just the main elements. So this is a picture that for people in quantum information is very common. So we have 3 stages, and this that in GPTs we will call procedures. And these are the preparation, the transformation, and the measurement, which are the 3 pillars of the operational description. And in particular, what I would like to stress is that for like outside the quantum information community, we tend to disregard a bit the set of measurements, but it turns out that if you want to characterize fully the nature of a physical system, then measurements are really important. So we really need to take into account the full set of measurements, because if you do not do that, you might be led into thinking that your theory has different features from the ones that it actually has. For instance, the simplest examples is if I take a qubit and I only measure on the Z, in the Z direction, so I only measure sigma Z, one of the Pauli operators, this is operationally equivalent to a classical bit. But in fact, I have a qubit, and if I had measured also sigma X and sigma Y, I would have realized. So a GPT system, we call it S, and it's the object that we will work with, is a system that is agnostic to the specific description of the system itself. So it doesn't know whether it is classical or quantum. It can be anything, it's just general. And it's characterized by these 3 procedures that are described in terms of operationally equivalent statements. So the set of states is the set of operationally equivalent preparation procedures. Then we have the set of linear transformations on these states, which can be the dynamics, but it can also be things that I act upon, like pressure and temperature. So it can be different things. And then I have the set of effects, which are the operationally equivalent measurement outcomes. And in our case, what we are going to do is to put some constraints on the set of effects. And this will determine whether the theory is classical, quantum, or something else.
Can I ask a question?
Yeah.
What do you mean by operationally equivalent?
That I cannot distinguish it in terms of probabilities.
Okay. I mean, like when you say operations, what operations like mean?
Like operations that I can do in the lab. I don't know, like I put a mirror, a beam splitter, and I split the 2 outcomes, and then I measure correlations between these outcomes, or yeah, things like that.
Okay. Okay. All right. Okay. Thank you.
Well, okay. So this brings me to the no-go theorem. And just let me just read it. So the no-go theorem states that we consider 2 non-classical systems, A and B, initially in a separable state, and the gravitational field G. We assume that the systems A and B only interact gravitationally. Then the following statements are incompatible. The first one is that the gravitational field G is able to generate entanglement. The second one is that A and B interact locally via the mediator G. And the third one is that G is classical. So this, we have to give up at least one of them in order to have, we have to give up one of them. So the first thing that I would like you to notice is that here we have non-classical, which doesn't mean quantum. It's a general thing, it's a more general thing in GPTs. And And then I have these two words that are unfortunately not very visible here, mediator and classical, on which I would like to say a few more words. So the mediator of local interactions, we mean it, so by mediator, we mean really the GPT definition of what a mediator is. So we have three systems, A, G, and B. And the most general interaction is written in terms of a series of interactions, of pairwise interactions between A and G and B and G. And we can put as many of them as we want, but A and B do not interact directly, they only interact via G. And the other thing that is relevant to us is that usually when we want to learn the properties of a GPT system, then we're just going to measure the system on its own. But here we cannot do it with gravity, it's too hard. So we cannot measure gravity directly. And so what we're going to do is to infer properties of G by making measurements on A and B. So that's also a difference compared to the standard description. And then the other important thing is what we mean by classical. And here we try to take a definition that is as close as possible to the standard textbook definition. And so we have two components to say that a system is classical. One is that it is, we call it kinematically classical, which means that any two pair of states can be perfectly distinguished. And the second one is that it is compositionally classical, which means that it composes with the standard tensor product rule with other systems, whether classical or non-classical. And then let me just remark that in GPTs, non-classical does not imply quantum. Usually we are used to thinking that classical and quantum is just a dichotomy, and one, if you negate one, then you have the other. But in GPTs, this is not like that. And we have a much richer structure where classical and quantum are just two instances of a theory, but we have many other options. And in particular, options, some options, you can rule them out because they do not interact consistently with classical and quantum theory. So if we want A and B, if we want to restrict A and B to quantum systems, then gravity has to be a system where after the interaction with gravity, we are left with the same initial space for A and B. So this already excludes some of them, but there are some cases of GPTs, and I'm not an expert about that, which interact consistently with and are neither classical nor quantum. So that's another advantage of GPTs, that they are a well-studied framework. So we can give many examples of mainly time models, and maybe they don't have a lot of like connection with things that we know are real, but at least they allow you to thinking in more abstract terms and provide explicit models for that. Okay. And then another thing that we looked at is how alternative models of gravity fit into our noble theorem. So, because again, this is, since we have a theory-independent framework, then we're not committed to any description of the gravitational field. So we can change it and we can see what happens when we apply it to our noble theorem. So the things that we looked at are gravitational decoherence collapse models and a GPT model that would correspond to the Schrödinger-Newton, and I will explain that in a minute. So let's remember the three conditions that are written up here. One is the generation of entanglement. Two is local, like the gravity is the local, A and B interact locally by the mediator G, and the third one is that G is classical. So gravitational decoherence is basically described as an effective field theory of the gravitational field that, however, makes the system decohere because there is a graviton bath, basically. So it's like an environment, gravity acts as an environment, so it decoheres the system. So basically what it does, so gravity is operationally classical by this definition, but it interacts locally, but it does not generate entanglement. So this is how gravitational decoherence fits. It's a quantum model, so it's easy to fit it into the no-go theorem. And the same goes for collapse models, because they are also quantum, basically a quantum model, because collapse models only have nonlinearities at the level of the state vector, but at the level of the density matrix, they can be written as an open quantum system. And so again, they would not generate entanglement, but they satisfy the other two conditions. For the Schrödinger-Newton equation, the situation is a little bit more tricky, because the Schrödinger-Newton equation is very well known in the one particle case, but when you compose the tensor product of two systems, then we do not know what the tensor product of the composite system would be. So we cannot univocally build a tensor product, and this has not been done. And in particular, so there is a very technical reason for that, which is that it has been shown actually in the 70s that the state space of a system that obeys a Schrödinger-Newton type equation is classical. So it is basically a classical system. And so it has to be shown that how two of these classical systems that, however, you still want to have entanglement, because that's what they say in the Schrödinger-Newton literature. So it still needs to be shown how this composes. So the best we could do is to think of a GPT model which would correspond as closely as possible to what a Schrödinger-Newton description would be like. And in this case, if such model exists, then it would violate condition 2, which is the fact that A and B interact locally via the mediator G. And the reason is that the Schrödinger-Newton equation knows about the wave function everywhere. So you can generate entanglement. Gravity is still treated as classical, but this entanglement is not due to the interaction with G and the single parts, but is due to the fact that the wave function has this non-locality and that acts really at the level of the dynamical equation of motion. And then, of course, there is the usual treatment of gravity, like linearized quantum gravity, for instance, which has a non-classical gravity, and yeah, and that's easy. Okay, so basically, this is everything I wanted to tell you. And let me just give you some final considerations on where we are now. So the first question is, where do we stand in our understanding of the nature of the gravitational field with these tabletop experiments? So there are two opposite views. One is, well, you cannot say anything because it's just Newtonian interaction. And the other one, no, actually you can explain this effect with gravitons, with off-shell gravitons. So this is my personal opinion, but there was also a recent paper that says the same thing, so I'm not alone, is that we stand a bit in the middle. So it is a bit reductive to say that the Newtonian field, since you have interaction with the Newtonian field, you cannot say anything, but it's also too much to say this is graviton effect. We do not know exactly where in the middle we are, and I think that this is what we have to clarify now. But I think that there are many exciting research works that are coming out on this topic now, and to really pinpoint where the problems are and where exactly what we can claim on with these thought experiments, and which will become real experiments, of course. When I talk about thought experiments, I'm hoping that they will be realized. And then if we want to really clarify this thing, what do we need to do? So I think we also need two different approaches that are both valuable and for different reasons. One is a precise formulation of the protocols and experiments using a concrete description of the gravitational field. And this is because such a formulation would allow us to emphasize the quantum aspects of the description and to which are actually very important if we want to know what is playing a role in deriving the effect, that we're not misunderstanding something, basically. And also, I think that one very important and interesting topic is that, so now the view is that it's actually the fact that spacetimes are in a superposition that is actually playing a role in describing this gravitational induced entanglement. And so it would be interesting to be able to relate in a more concrete and formal way the superposition of massive objects to non-classical spacetime, and which properties of non-classical spacetime can actually brought out in this type of experiments. And then on the other hand, so that's using a specific formulation, but on the other hand, I also think that a theory-independent description could help us in different ways. And I think that, so what I like to stress is that I do not think that the theory-independent description is valuable because we are interested in showing that gravity is neither classical nor quantum. But I think that the value of a theory-independent description is that it's robust against modifications of the theory. So it's like Bell's theorem. We are not interested in showing that quantum theory is wrong or that there is an alternative description for that. But we want to know that if it happens, then that for some reason we find that this AM, even A and B, but even G is yet something else. It has different properties. Then we can still apply these results because they would still be valid. In addition, another very important property a feature of GPTs that is built in the framework is that they give you for free a fully consistent verification of the internal consistency of the theory. So, because you have constraints when you put these three procedures together, preparation, transformations, and effects. And so when you basically, when you consider all of that at once, then you automatically verify that everything is consistent. And also because they allow you to classify alternative models, and so hopefully to rule some of them out experimentally once you verify the effect. And this is all, and I would like to thank you for your attention. And yeah, that's not Waterloo, of course.
We do have views across the water like that in Chicago, but
yeah,
not for both buildings.
But that's Toronto.
Okay, thank you so much. That was really very enlightening. That was a great talk.
Thanks.
So I will take, so usually what we do is take questions from people in Geneva or Switzerland first, if people have some questions there, and then maybe I'll take a few Zoom questions, and then we'll do some questions in the room. So can people indicate they have questions by either putting it in the chat or by raising virtual hands, because I'm looking at the list of participants. And I assume everybody can hear me okay. Oh, Chris has a question. Sorry, yes, which is indicated by writing question. Okay, go for it, Chris.
Should I go ahead?
Sorry, yes, please.
Okay, thank you very much. Thanks, Flaminia. That was very interesting. I have a question that sort of comes from an immediate philosophical reaction to what you said when you said that what we're seeking is a theory-independent description. My gut reaction is, well, there is no such thing. Sorry, that's just any description will presuppose some theory. And of course, the very first thing you said when you said that you're seeking a theory-independent approach. How do you do that? Well, we use the framework of generalized probabilistic theories. So in some sort of trivial sense, of course, that's not a theory-independent approach. It presupposes some theoretical framework. And now the more serious question this raises for me is, what exactly, what is the relationship of that theoretical framework to maybe specific quantum theories of gravity that we might want to articulate? That's the question I'm interested in. And I'm thinking what you seem to have in mind is that this is, even though strictly speaking a theory, it gives us a more general framework in which we can sort of embed or articulate some of the things that are going on in a way that should be neutral between actual competing theories of quantum gravity. And so I would like you to tell me a little bit more about that. And then also specifically what that means is you did give some examples of which kind of theories are violating which of your three conditions of in the no-go theorem. And I would be assuming that if I understood correctly what you're trying to do is that most of the most prominent approaches to quantum gravity would be violating condition 3. They would deny that gravity is classical. Is that right?
Yeah. So yeah, concerning your question, so I think we still have a long way to extend the no-go theorem, because usually this is all done with finite dimensional Hilbert spaces. So this is also a very typical quantum information approach where you have a very complicated space and then you restrict to just the degrees of freedom that matter for you. And then you map that onto a discrete description. So that's what we are doing here. However, these tools can be generalized to infinite dimensions, my collaborators say. In order to really show, so we had some discussions on the possibility to describe GPTs, for instance, in quantum field theory. And I think that people that are more actively working on GPTs are very interested in this possibility, but that's something that has not been done yet, and that has a lot of technical obstacles, basically. So to describe a quantum field theory in general probabilistic terms. But it is something that people are thinking about. And then concerning your first, so basically the answer is that my gut feeling is that yes, approaches to quantum gravity would violate 3. So that the fact that gravity is classical, but I do not have a proof for that. Because this also addresses a low energy regime where it is also hard to take so there are attempts of taking the low energy limits of quantum gravity approaches, but that's something that is not fully clear, or that it's complicated. And so there is this interplay of different obstacles. And then concerning your first question, yes, it's true. We are using a framework. I think at some point is also it's also personal taste of what you are willing to accept when you want to do a description, when you want to describe something. So from my point of view, accepting just the operational level is not a very strong commitment. Because that's in any case what we will be able to observe in an experiment. We cannot do without that. We learn about the world by looking at the outcome of experiments. So for me, that is an appealing way to proceed. But of course, there could be other approaches, and I think after a certain point, it's also really what it matters to you personally to accept, and what you're willing to accept and what you want to give up.
Thank you very much. Can I follow up?
Mm-hmm.
So thanks. That was very, very very, very helpful, I have to say. So maybe would you agree then that if I understand it correctly, what's going on is you mean theory-independent approach in the sense of that you don't sort of start out from basic physical principles that would normally be considered like defining or characterizing our main theories, but instead you're trying to come up with a sort of an operational description of an experimental situation that you believe that doesn't make any commitments about physical principles that go beyond sort of the bare minimum that you need to assume about the experimental situation.
Exactly, yeah.
Okay.
You only rely on your probabilistic description, which is basically what the outcome of the experiment is telling you. And then you can constrain the theory behind that by looking at the experimental outcome, basically. That's what I mean, yeah.
Okay, great. Thank you very much.
So I think I will ask a question then, but you know, other people, please do come and ask questions. So I really liked the first part of the first sort of half of the talk, or the first paper that you talked about with Valenkia, that you know, and that you and other people wrote with him. I really liked the way you kind of made the conclusion there, where you had something along the lines of the Newtonian potential. What we're supposed to conclude is the Newtonian potential has quantum information content, and hence its own quantum state. Because you know, Mike and I and Niels sort of spent so long kind of trying to figure out exactly what the conclusion of the paper was, and so how it kind of bears on the gravitationally induced entanglement experiments. And that actually is like, we never came up with anything kind of quite as clear as that. I think that's a real thing, Mike. I mean, I think it's a really nice way of kind of saying how we're supposed to go from, you know, the experiment that you described to the sort of BMV kind of experiments. But still, I'm not sure I'm totally convinced that it quite does ultimately. So this is to sort of respond back that there's still some ambiguity here about what the BMV experiments would show, where you have, you know, you talked about at the very beginning.
Well, the BMV doesn't have retardation.
Right. So what I would say is, look, you know, no one disagrees that the gravitational field ultimately, fundamentally, is quantum. It's a quantum state, and that maybe there are even circumstances where that's true of the Newtonian potential. What's really at stake is whether the BMV experiment is actually seeing that quantum information content. And why should I think that? Because it is different. You know, I don't actually need all the full apparatus from the Valenkia experiment in the BMV experiment.
Yeah,
so I could still put my foot down. You know, I dig my heels in and say, I'm not seeing it yet in this experiment.
Yeah, no, I agree with you.
Okay.
But I wouldn't.
No, this is a philosophy talk. You're supposed to argue.
No, okay, but maybe I would shift the question from like, not because the BMV is a particular instance of an experiment that could be realized. And I would shift the question to which is the best experiment that we could potentially realize in the future that is able to bring out these features. Right. So I'm not really concerned about the BMV. I think it was really it was a nice result because it had many merits of its own, but to me, this is not what I want to show that brings out the features. I want to know which experiments would bring out these features. And this is also why I think that all these investigations, also the theory-independent ones, can come useful, because then you can really pinpoint to which type of element you would need. And then you can try to use that element to make an experimental setup and to devise an experiment that would bring out that feature. So to me, the question is more general.
Okay, oh, that's great. Because actually when we were reading it, that's kind of the place I would keep going to as well. It's really like, what would the Valenkia experiment
Yeah.
If I could do that, what would I show? And that one way of reading that seems to be you get gravitational, you get actually decoherence because it's interacting with the gravitational field. So whatever. Alice doesn't see coherence anymore because, okay. Oh, well, that's great. Okay. Oh, good. Oh, yeah. Okay. Very, very, very nice. I'm very happy about that. Yeah, that's great. Well, there's more questions and we can talk some more. I got one online, so I'm going to take that and then I'll come to. Sorry, I didn't actually look at this end. Deepak, would you like to ask a question?
Yes. So my question is that the first two statements that you have listed, that gravity is able to generate entanglement, and then the second is that gravity locally mediates the interaction between non-classical systems, right? So you're saying that these two statements are incompatible.
No, the three of them. You can have 1 and 2, but violate 3, or you can have 1 and 3, but violate 2, or you can have 2 and 3 and violate 1.
Oh, okay. 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 Then I guess, yeah, that answers my question.
Okay.
All right. So thanks. Yeah, so I just want to understand better the import of your result by looking at, if you could help me look at an example, just take the non-classical theory to be quantum mechanics, right? And you just consider spins or something like that.
Sorry, you're talking about the second part of the talk or the first one?
The second part.
Okay.
Yeah. So your no-go theorem, right? Where you're trying to rule out the trilemma, so to speak. And I'm just trying to, so can you sort of give a quick example where A and B are quantum mechanical systems, right? And maybe their states are qubits. And so what is that? And forgetting gravity for a second, just what kinds of interactions am I ruling out? So for example, if I just have two spins and I have a sigma z tensor sigma z interaction, then that will get me entanglement, right? But I don't really think of that as being mediated by any third system in a way.
Yeah, exactly. You are giving up the second one in this case.
Right. But is there an example where, I don't know if I can phrase my question better, but I probably can, but I don't know how to. But so is there an example? Can you give an example of a mediator in a quantum theory? What would a mediator look like? So if I just have a third spin, is that?
Yeah, for instance, yeah.
Okay, but how? Okay, so if I have A, B, and C, with a sigma z with A and C, is that also, do you count that as local?
Sigma A, sigma C, no.
But, okay, so can you help me understand what would a local interaction would is that just a, I mean, if it's a unitary between A and C, then that can be sourced by something like sigma A, sigma C, right?
Yeah, so basically you can think of these as two spins and this is as the third spin.
Right.
And then your interaction Hamiltonian will be just made up of terms that are sigma A, sigma G, sigma B.
Right. So but you count those as local?
Yeah.
Okay.
Yeah.
But then if I just have A and B, and then I have interaction between them, that will also generate. Yeah. Okay.
You do not have interaction between.
No, you don't. But if you did.
If you did, yeah, this would also generate entanglement. But yeah,
okay.
But this would be like the equivalent of having like the spring before with the, which has an interaction potential that is, I don't know, like k divided by 2 xb minus xa squared. And then if you generate entanglement via that potential, you're not saying, okay, this potential actually corresponds to a degree of freedom that is quantum by itself, that has its own dynamics, and that, I mean, that's a much heavier statement to make. So by just generating entanglement at that level, you cannot deduce that of this harmonic oscillator, basically.
Okay.
But yeah, of course, you can generate entanglement with that.
Right. So then what of the trilemma, which one are you giving up the?
We are not proposing a solution. We are not saying what gravity should be or should not be. Of course, like our secret hope is that you will be able to give up 3.
No, of course, no, yeah.
Also not that secret.
Okay, maybe here's another way to ask my. Can I just quickly follow up?
I was going to say, if you do the experiment and you see the entanglement,
exactly.
then you know
already
one's true,
one
so then you've got to choose
gone.
between 2 and 3.
Right.
But I think so. The setup on the slide where you have the trilemma, there's conditions that were stated in the sentence at top that I think is what you're running to.
What were the conditions here?
I mean, hardly conditions, but you have 3 total systems, or more than 2 systems, and that A and B are separable.
Right. Okay.
So maybe I was misunderstanding what you were getting.
Yeah. So I don't really have an objection or anything like that. I'm just trying to understand better, another way to ask it is, if I just think about quantum mechanics, is there a way of stating this result that's somehow more familiar? Like, is there a familiar theorem in quantum mechanics that has the same content?
It's the LOCC theorem, basically.
Okay, but you can't generate.
Yeah.
Right. Okay.
So the way you prove this result is a generalization to GPTs of the LOCC result.
Okay, that's very helpful. Okay, thank you. That helps a lot. Now I see what you're saying.
Okay.
Great.
So actually, Deepak wanted to follow up on
Yeah,
his
thanks.
question.
Sorry, I'm not able to ask all my questions in one go because there are a lot of subtleties in these arguments, and I'm trying to figure out what's going on. So then the statement is that 1 and 3 are compatible, right? That gravity can generate entanglement, and it can also be classical. But that doesn't make sense to me. Like, how? I mean, just if I just think about 2 quantum systems and I want to, mediate entanglement between them, or how can any classical agent do that? How that is the thing that I don't understand.
Yeah, you would need to have a very strange model to be able to generate entanglement with a G that is classical, such as, for instance, Schrödinger-Newton, where you have that basically the state goes into the dynamical law, and so at some instance of time, then you know the quantum state of the whole system anywhere. So that's enough.
Is the Schrödinger-Newton system an explicit example of such a system, which is classical but which can generate entanglement?
Yeah. So
didn't you say that the Schrödinger would violate 2?
I would say that the Schrödinger would violate 2. Yeah.
I think perhaps can I put a finger on? I think perhaps what he's saying is it's kind of weird to say if you have 2 and 3 are true, then it's because they're only A and B are only interacting locally via G.
Sorry,
I
didn't get this.
I'm just trying to understand the possibilities that you're saying are correct or can hold.
So if you want to keep 1 and 3, so you want to keep the possibility of generating entanglement and the fact that G is classical, then you need to violate 2. And this means that your mediator is classical, but it's not the thing that is responsible for the entanglement, basically.
No,
so you need to have another mechanism.
But then there is no explicit model of any system which satisfies these 2 conditions, is there?
So we believe that so if there is a GPT model for the Schrödinger-Newton equation, which is something that we are not sure about, then this is a model that would satisfy what you're saying.
Okay, all right.
So that would violate 2 and keep 1 and 3.
Okay, thanks.
But we don't know whether this model, whether this model exists. but this would be the closest thing to what you're saying.
All right, thanks.
I have a finger here, yeah.
So is Bohm mechanics an example of?
I don't know. We at some point this came out in the discussions, but we got confused because we realized that some people don't even agree that whether to call it classical or quantum, and then we gave up.
Okay, but yeah, there is this non-local thing that mediates
Yes.
that generates entanglement.
Yes.
Right. Yeah. Okay. But yeah, I don't know. I don't know if it also falls into the GPT model.
Yeah, I don't know either. Yeah.
Okay. So let me take one. This has been up for a while. So Pascal.
Yes, hello. Thank you for the presentation. So you have got a no-go theorem, and we have to reject one, at least one of the assumptions, right? But the fact that if we reject three, and we assume that gravity is not classical, that doesn't mean necessarily that the other two conditions hold, right? I mean, we could have
correct.
Quantum gravity and non-locality. Do you think it's worth to explore those options, or we should reject them by other reasons?
No, I think that this is a very meaningful way to proceed. So this was just the first result, and we had many questions ourselves. So at some point we just had to focus all our confusion into something that fit in a paper. And that was already pretty hard. But I think that there are many possible ways to go now from these. And what you're saying is definitely an interesting option. So to find how you could also if you can vary some of the conditions and put them in a different way, so that maybe other specific features would come out, like faster than light signaling or non-locality or non-linear dynamics. All these elements are definitely interesting to look at and to see how they can be phrased.
Thank you.
Bruno, nice to see you, by the way.
Oh, well, thank you. Great talk. I have just a clarification question about this no-go theorem, particularly when you define what a classical theory is. You mentioned that it has to be, states have to be perfectly indistinguishable. And I was wondering what perfectly distinguishable state is. How would you describe? Do you have a counterexample? If you could comment on that.
Yeah. So if you think, for instance, of the throw of a coin in classically, you throw a coin and you get either heads or tail. And with each single throw of a coin, you know just by looking at the coin whether you got head or tail. So that means that it's perfectly distinguishable. In quantum theory, this is no longer true, because if you think of any qubit state, then you cannot fully characterize your state with just one measurement. And you can only perfectly characterize one quantum state with a single measurement if, for instance, you have 0 or 1, and then you measure in sigma z, for instance. And then you know that for sure you got either 0 or 1, and hence you have 0 or 1. And the other one is orthogonal.
So you're restricting the number of operations that you were allowed before?
So perfectly distinguishable means single shot, basically.
Thank you. Okay, that makes sense. Right. Yeah, because otherwise, well, in any case, because if you had multiple shots, you're destroying the state anyway, right? Oh, yeah, that makes perfect sense. Thank you.
Okay, Mike?
So I have a couple different questions that are unrelated to each other. But I guess the first, or the big one I'll ask, is primarily just an invitation to hear you muse on your perspective. So in response to Nick's question about your paper with Valencia and the others, right, so there was this really nice punchline that you said, which was something like, the question you're interested, or something you're interested in, is what is A, or what is the first experiment that we could one day hope to do tabletop that will really get at the quantum information theoretic content of the gravitational channel on supposition that it is, etc. One thing that we ran into when we were thinking through and wading our way through the back and forth disagreements was a rather trivial observation that we never knew what to make of it, which was whenever we're writing down even the most basic Newtonian expression for the BMV experiments, you've already had to put a little hat on your phi field, on your potential. And so the trivial point was, in some ways, we've already, like, we can't even get off the ground without seeing the quantum content of the gravitational channel, even when it's just constraint, even granting everything to sort of the other side in this dispute. It's still an operator, it's not a field in the class. Presumably, you're not already on board with that sort of trivial, like, look, it's already quantum, because you're interested in the Newtonian with retardation as the first regime where we genuinely see the quantum. So yeah, like, what's your perspective on why is that not enough?
So basically, the fact that you are basically already forced to at least write a state for the gravitational field, because otherwise it just cannot. I mean, it doesn't make sense to compare, right? This is your question. Yeah. No, so that's a big problem. So one thing that is basically a corollary of the thought experiment that I presented, the Belenkia et al. That one is that if you try to repeat the argument without writing down a quantum state for gravity, then you run into faster than light signaling. So that gives you, because basically you need the state to emit, to be able to emit radiation when you recombine it in order to save yourself from the faster than light signaling. So if you do exactly the same the derivation, but without ever writing associating a quantum state to the Newtonian field, then you're back into faster than light signaling. So I think at the moment, this is the best motivation that I can give you for considering even the Newtonian field as a quantum system, well, as a system, say, because we don't want to say that it's classical or quantum, but if it's not even, if you don't even allow it to have a quantum a state of its own, then you for sure run into faster than light signaling. So that's the, but it's true that I wouldn't consider that as fully subdued.
I already asked that.
I have a question. I think I misunderstood something important before. When you say that when you give up 2, and you say then that G is classical, then you say that it's not then the gravitational field that will generate, that actually generates the entanglement, but then 1 is not correct as well.
No, so say you want to give up 2, and then you can keep gravity classical, then 1 can be either true or false.
Okay.
You can have both. Okay. So you can either have a classical field which does not generate entanglement, and that's totally fine. That's actually the most common and standard thing that happens usually. Or you can also have a gravitational field which generates entanglement, but then it's a very strange model, like the Schrödinger-Newton. So it's, but it's also fully fine that you violate 1 and 2. So the G does not generate entanglement, the G does not, and A and B do not interact locally via the mediator, and the G is classical. That's fully fine.
Does this have anything to do with the question of the true degrees of freedom that you were mentioned before?
So we try not to phrase it in these terms, because we try not to assume any specific description of the gravitational field. But it is motivated. So I think that it's actually a bit so this true degree of freedom is a kind of a confusing question to ask, because the Newtonian field is a gauge degree of freedom only in a certain gauge. But then if you change gauge, then your description looks totally different. And then it's mixed with the others, with the radiative degrees of freedom. So the splitting is totally arbitrary. So that's a very strange, I don't know, I don't feel comfortable using this splitting between real and gauge degrees of freedom in order to make an argument, because it's an arbitrary splitting. So one would like to have a more like an argument that is independent of this arbitrary distinction.
Yes, okay, thanks. Yeah, so I'm curious about what you think about entanglement that comes from symmetry. So if you think about the Helium atom, right? There's a classical field, right? The Coulomb field is classically treated. The ground state has entanglement, right? And I don't see any non-local interactions there. So prima facie, it looks like a counterexample, but I imagine there's something that I'm missing there.
Okay, so I didn't, but what is the fact that the generation of entanglement here?
Well, it's because they're fermions, so they have to be antisymmetric.
But that would be equivalent to the choice of the initial state for us.
Can you say more about that?
So here we are taking the initial separable state, and then it's the dynamics that generates the entanglement.
That's okay, right? I can start out 2 electrons. Oh, I see. So you're saying because they're fermions, they always have to be non-separable.
So it's basically, we wouldn't be in the initial conditions of the theorem.
I see. Okay. Okay. So, right. Okay. Yeah. Great.
I mean, of course, we have a strict condition here because we wanted to be on the safe side. We could relax that a bit. So the reason why we have such a strict condition is that there is a recent result that says that one should be careful on some initial states, not all of them, but some initial entangled states, then it is not meaningful, like the generation of entanglement is not meaningful. But you can have basically many entangled states also at the beginning, just not those particular ones that create troubles. And so, but we wanted to be on the safe side and say, okay, it's separable. But of course, then, I mean, there are ways in quantum information to measure how the entanglement changes in time. So that's also fine.
Thanks.
Okay, I'm going to ask a second question, which was, I think, on the very last slide where you were talking about, but not the one where you showed us the picture of Seattle or whatever. The one before that, where you said about the future. One of the questions you asked was about, you wanted to say that one of the things you wanted to do was relate particle quantum superpositions to non-classical spacetimes. Could you say a bit more about what you had in mind there? Because I wasn't. Did you just mean superpositions of spacetimes, or something more than that?
So my ambition is to do a little bit more. So okay, so basically one of the assumptions that we have here, because we do not have a full theory of that, is that we can superpose linearly basically classical results in a superposition, because we have these two macroscopically distinguishable configurations of the gravitational field. So this means that the gravitational field on the left and the gravitational field on the right are orthogonal in quantum theory. And then we can identify each one of these states of the gravitational field as the most classical-like state of the gravitational field that we could derive within a quantum approach to gravity, so like a coherent state of the gravitational field. And then we can think that we could relax this condition. So what happens now if we have a quantum source, but this quantum source is written in a way that, so we cannot split it in these two amplitudes of the gravitational field that are respectively orthogonal, but there is some overlap between these two states. Then we wouldn't be able to just apply results in like classical results in a quantum superposition, because this is a more complicated state of the gravitational field. And I think that there maybe there is something interesting to be found also in terms of effects.
So I got that idea. So, but couldn't I still? So now I've got kind of, I'm imagining sort of two wave functions for the gravitational field, and they're overlapped. Oh, I see. Yeah. Okay.
Yeah.
Right. Yeah. Okay. Sorry. Yeah, I see what you're saying. Okay. All right. Interesting. Yes. 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 Mike, did you have your second question?
Yeah. So there are two ways of understanding the advocacy for the GPT's framework for this result. I'm interested in which one or maybe both that you like. One is that this is a very nice bare bones operational approach to these questions. We have the conditions that go into the framework itself have a lot of intuitive pull, and so we're going to proceed trying to prove our theory-independent results with this framework. A different one, and because you mentioned like the sort of constructor theory, that other sort of no-go type results are proven just in a different theory-independent framework. That opens up a different sort of virtue or a different way of understanding why we would want results in here. Some sort of robustness appeal that, well, every way we can think of to write a theory-independent framework, we can find a similar sort of result. So there's some robustness across these different frameworks for the laboratory operationalization. Which of those would you embrace?
So I'm open to having other different theory-independent frameworks. In the specific case of constructor theory, there are quite a few differences. So for instance, for A and B, they consider just qubits, and they cannot consider just general non-classical systems as we do. Then constructor theory, by assumption, assumes tomographic locality, which means that it's the property that you can reconstruct the full states by making measurements on the subsystems. And this is, for instance, this property is not verified in many examples of GPTs. So there are GPTs that violate tomographic locality. And they also assume subsystem independence, which we do not assume. And then they have, it's also like, well, GPTs have this very operational, like they are an operational approach. Instead, the constructor, so I'm not an expert of constructor theory, but what I try to understand with the, so constructor theory makes also some more ontological commitments, in particular with the definition of gravity as an information medium. So there are, in this case, there are some differences, and I think this would reflect your attitude towards these problems. So I'm not saying that one is better than the other, but I think according to your preferences, you might prefer one or the other, according to what you want to give up and what you want to preserve, and what your philosophical stance is also.
And then, given that your particular sense of GPTs are in fact the more general or more purely operational.
Yeah. Yeah.
Okay, do we have any kind of more questions? We're nearly sort of out of time. There's time for like one or two more questions if people have them. I think you want to go again?
Yeah. My theory is entirely unrelated to the first two questions that I've asked. In this approach, so this no-go result, if G is in fact a conglomerate, a giant tensor product system itself, so that's I would presume that's no problem for this, but it might be the case that there are going to be further physical principles that make us want to say, well, one part of that is gravity, and it's in fact not playing the relevant roles, and so it's still classical, but it's this mysterious other hidden force or hidden interest.
Yeah, you could play this game, yes.
Okay.
Yes.
And playing this game would be presumably frustrating to you or to this style of approach, because it's going to force you back into the physical principles conversation.
Yeah, well, maybe not that. It wouldn't force you back into the physical principle, but it would allow you. So the more you specify about gravity, the more you are putting into your. So if one thing could be, for instance, I make a spin model of the gravitational field. So since I know that the gravitational field is an extended object, I want to just put a spin for each spacetime point, and then I discretize my spacetime, and so I have a chain of systems for each one, and then I can work with that. That's a model of the gravitational field. That's a reasonable one. It would, I mean, the complexity of the argument would scale, because then you would have to say how each spin interacts with the neighbors, and how you would build a full chain of interactions between A and B, and how so it is. It would be technically more complicated, but I think you could do it.
Well, I will sort of follow up just a little bit, and because we have a couple more minutes. When we were sort of thinking this through and trying to understand some version of LOCC sort of theorem, so we kind of came up with a sort of simple kind of version of that sort of proof that really, works. It's more specific because it kind of just adopts a particular Hilbert space and kind of there's a So, but when you think about it in those very concrete terms, the theorem seems to rest so much, or our version of the theorem, or kind of toy version of the theorem, I guess would be a reasonable way to say it, seems to turn so much on it's just very hard and awkward to represent it something as classical if you've already got the quantum framework. And so you don't feel that it's that, you've got quantum mechanics, so, classical, you're so hobbled. So do you agree with that assessment? And then things like the theorem you're doing in a more general framework are really what you do need to do to kind of actually
I agree.
Say something here.
I think it's the same type of frustration that one gets when you explain the electromagnetic version of this, and nobody complains because we already know that electromagnetism is quantum. And so why would we need to bother with a classical definition at all? But then, of course, it becomes interesting when you put the gravitational case, because then everybody complains.
Right. Okay. Very good. Very good. Well, that is about the end then, I think, unless anyone has any short final thoughts. That's about the time we have. So I just want to say thank you again for what a great talk and great discussion.
Thank you very much.
Really appreciate it.